Imagine, just for a second, trying to guarantee that exactly 2 billion things happen perfectly on time every single day. No delays, no skipped tasks, absolutely zero duplicate fires, just 2 billion flawless executions. I mean, we're talking about the billing retries at major fintechs, the massive batch jobs crunching your data overnight, and pretty much every single send this notification at 9 a.m. feature you've ever used. That is the sheer, mind-boggling scale of the challenge we're tackling today. We're looking at the definitive engineering blueprint for the system that literally powers the scheduled background work of the modern internet. But before we even think about drawing a single box on a whiteboard, we have to talk about a fundamental architectural philosophy. This is the exact insider mindset that separates the senior staff-level engineers from the juniors. It's this: never, ever confuse where data lives permanently with where data moves quickly. A database like MySQL, that's your durable truth. It's optimized for holding state, making sure data integrity is rock solid, and running complex time-indexed queries. On the flip side, a message queue, like Kafka or SQS, that is your fast truth. It is strictly a transport mechanism, not a store of record. And keeping these two concepts entirely separated, that is absolutely crucial. It's the core secret to scaling your systems to billions of tasks. So welcome to this explainer. Today, we are going to deconstruct the invisible engine of the modern internet. Relying entirely on our source teardown, we're going to look at the blueprint for a distributed task scheduler built for true Google scale operations. We're going to strip away all the magic and look at the exact mechanics of how to build this properly right from the ground up. Here's a quick look at our roadmap. We'll hit the core problem, the 6-tier blueprint, the puller magic, the SLA latency budget, surviving chaos and failure, and finally, the interview masterclass. Let's get right into it. Part 1, the core problem. Okay, let's dive into this. Every modern internet product essentially runs on deferred work. Think about it. When a bank charges your subscription on the first of the month, or an unpaid ride-sharing trip is automatically abandoned after exactly 30 minutes, that is a scheduled task. And if the scheduler is late, literal money is lost. It's the canonical hard problem in system design because it forces you to confront full distributed primitives like sharding and queues, strict latency budgeting, and crucially, idempotency. Idempotency is that absolute guarantee that a task, like a bank charge, happens once, and only once, even if the network blips or a server crashes halfway through. There is simply nowhere to hide bad architecture here. Part 2, the 6-tier blueprint. Let's actually build out the infrastructure framework. So this is the 30,000-foot view of how a task flows through our system. It starts completely stateless right at the API tier. Then it gets saved in the storage tier. Now, this isn't just any database. We're talking about a sharded MySQL fleet, strategically partitioned by tenant, so no single noisy customer can bottleneck the entire database. Next up, our puller tier extracts the tasks that are due soon. They drop these into the queue tier, which elegantly decouples the extraction part from the execution part. Then, the executor tier actually steps in and makes that final HTTP call to the client endpoint. And overseeing all of this, the orchestrator. It uses a tool like ZooKeeper to manage leader election, basically making sure that if an orchestrator node crashes, another node instantly detects the failure and takes charge. No stepping on toes, no duplicated work. It really is a beautiful orchestration of 6 independently scalable tiers, each with one very specific isolated job. Part 3, the puller magic. We are now zooming in on the single most highly contended bottleneck in the entire system. So how do we actually extract due tasks from the database without creating a massive traffic jam? Well, the magic here lies in a very specific SQL clause. For update skip locked. Seriously, without this, if you have 10 pullers querying the database simultaneously looking for due tasks, 9 of them just have to sit there and wait for the first one to finish. You're essentially serializing your whole multi-million-dollar server fleet into a single thread. It's an infrastructure nightmare. But with this clause, concurrent workers can grab their own batch of jobs and just seamlessly skip over any rows that are already locked by other workers. It completely prevents head-of-line blocking and allows your extraction system to scale linearly as you add more machines. A real game changer. Let's apply a little interviewer pressure here. What happens if a puller process claims a job, updates the database to say, hey, I picked it, but then instantly dies before actually putting that job into the queue? Well, that job is now stuck in a permanently picked state. It looks like it's being handled, but it will literally never actually execute. In the distributed systems world, this little nightmare is known as the orphan job problem. The solution here is an absolute necessity for any highly available system, the Reaper process. Think of it as a background safety net that's constantly scanning the database for anomalies. If it finds a job that was marked as picked more than 60 seconds ago but hasn't moved forward to completion, the Reaper just assumes the puller died. It simply resets that timestamp, catching the lost task and putting it right back into the general pool so a healthy puller can grab it. And you might be wondering, why exactly 60 seconds? Well, as we're about to see, it ties perfectly into our strict latency budgets. Part 4. The SLA latency budget. This is where we shift to the rigorous math that staff engineers absolutely obsess over. Now, what's really interesting about this slide is how time is treated exactly like literal money here. Our service level objective, or SLO, which is our ultimate promise of reliability to the user, is a 30-second execution window. That is not a wish, guys. It is a rigid budget we must perfectly apportion. To track this, we use service level indicators, or SLIs, for every single hop in the chain. The puller gets 1 second to pick the task. The message can sit in the queue for up to 2 seconds. The executor gets a strict 10-second timeout to make the HTTP call, because downstream endpoints will hang and we absolutely cannot afford to leak worker threads waiting for a broken API. When you add it all up, our individual indicators comfortably hit that overall 30-second target, and we even leave plenty of buffer for network latency. Oh, and this is exactly why our Reaper from the previous step waits 60 seconds. It gives that 30-second budget plenty of room to finish its job before intervening. Part 5. Surviving Chaos and Failure. Time to pressure test this beautiful design against real-world production nightmares. Behold the 9 a.m. thundering herd. Because humans love round numbers, millions of daily cron tasks are scheduled to fire exactly on the hour. At 8:59, traffic is a trickle, but at 9 a.m. sharp, a massive, system-crushing spike hits. This happens because of a concept called cron materialization. The system suddenly has to calculate, generate, and queue up the exact next execution instance for millions of recurring tasks, all in the exact same seconds. If we don't manage this burst of materialization, the queues spike, our executors saturate, and our carefully planned 30-second SLA is blown completely out of the water. So, the absolutely crucial point is how we handle this sudden load. We use a really elegant technique called smearing. When a user schedules a daily 9 a.m. task, the system intentionally introduces a tiny bit of randomness, say plus or minus 30 seconds, at the precise moment of ingestion. The reality is, customers generally don't care about second-level precision for a daily email report. They care about minute-level reliability. This microscopic randomization flattens that massive traffic spike across a wider window and, quite literally, saves the entire infrastructure from collapsing under its own weight. But what if the threat isn't cron jobs at all? What if it's one noisy customer who suddenly schedules 100 million tasks because of a bug in their code? Without defenses, they would consume every single executor and take down the system for everyone. We build a fortress against this using layered quotas. We enforce API rate limits right at the front door, restrict pending job storage at the database level, group tenants to ensure puller fairness, separate traffic into distinct priority queue lanes, and place strict concurrency caps on the executors. This way, if one client's downstream endpoint slows to a crawl, it only backs up their specific queue lane. Everyone else's scheduled tasks continue to operate flawlessly. Part 6. The Interview Masterclass. Let's bring this explainer home. We're going to distill the architectural philosophies you need to pass a senior or staff-level interview. Before you ever pick up a whiteboard marker, you must walk through these 4 non-negotiable mental steps. First, calculate your hard scale numbers. Really understand your peak tasks per second. Second, separate your durable truth from your fast truth. Remember, your database is for time-indexed queries and your queue is just a fast transport. Third, rigorously map out how every single component fails, from dead pullers to hanging HTTP requests. And fourth, define your service level objectives and enforce a relentless observability chain using trace IDs across every single network hop. You must be able to prove mathematically through your observability metrics that your system is healthy across all 6 tiers. I want to leave you with this final provocative thought. A distributed task scheduler isn't just about running cron jobs. It is a masterclass in production-grade architecture. Whenever you design any component for any system, I want you to ask yourself these 3 ruthless questions. How will this fail? How will I know it failed? And how do I roll it back? If you can answer those 3 questions for every single box on your whiteboard, you are designing at the highest possible level. Everything else is just implementation details. Keep exploring, keep questioning, and I'll see you in the next explainer.